In this part 4 of the presentation about sustainability, we will review the reduction of carbon dioxide emissions by activities in the transportation sector. This will be followed by a discussion of some carbon-neutral cycle activities. The transportation sector can potentially reduce carbon dioxide emissions by 134 gigaton during the period from 2020 to 2050. Figure 22 show how this may be achieved, using a variety of technologies, such as hydrogen as fuel, electrical cars, mass transportation, and improved ships, trucks and airplanes. Significant developments and commercialization efforts are taking place in Europe, the USA, Japan, Korea, and China. Figure 23 provides a breakdown of the various technologies that can reduce carbon dioxide in the transportation sector. Hydrogen as fuel, electrical cars, and mass transfer will have the biggest impacts. This is followed by improved ships, trucks, and airplanes. Teleconferencing and electrical bikes are also mentioned, with relatively smaller carbon dioxide reduction potential. Future hydrogen car elements are shown in Figure 24. The fuel cell stack is applied as the car's engine. Below the passenger seats, one places a high-pressure tank for the hydrogen fuel. This shows a picture of a BMW hydrogen fuel cell car. The success of this and similar cars will depend on the price of hydrogen, ideally made by water electrolysis using sustainable electricity, not based on fossil fuels. Current fuels and chemicals are still largely made from fossil sources. In the industry sector, fuels and chemicals from sustainable resources can lead to a reductions of carbon dioxide emissions. It may take some time to transform the industry sector before industry will make their products using greener technologies, but several companies are already working on this and have shown great technical progress. Starting with carbon dioxide in the atmosphere, the carbon dioxide is used for growing trees, etc. The wood from the tree is converted to wood pellets. These can be burned to generate electrical energy, as shown in this case. By doing this, carbon dioxide is released and turned back to the atmosphere. This is a sustainable process cycle. It can be applied to lower carbon dioxide emissions, depending on the technology efficiency of the involved technological steps. A key question is, what will be the economics of such a carbon-neutral cycle? Instead of power generation, one may for instance consider producing a chemical in a rather non-efficient way, if one uses fossil crude oil as raw material. Biomass, municipal solid waste and other carbon-containing streams, can be used to produce biosynthetic natural gas, biojet fuel, green methanol, and green ammonia. This is schematically shown in Figure 27. In general, one needs a pretreatment step and gasification of the feed, followed by further cleaning and conditioning. Subsequently, a selected catalytic step can then make the desired product. Figure 29 shows how one can make aviation fuel from municipal solid waste, abbreviated as MSW. Of special interest is the Sierra project from Fulcrum in Reno, Nevada. Using MSW as feed, one first removes all non-carbon containing solids, like glass and metals. Subsequently, special gasification technology is applied, followed by Fischer-Tropsch synthesis, and product separation. The design product is aviation jet fuel, produced at a rate of 10 million gallons a year, from 200,000 ton of MSW per year. The Reno plant started production in 2019. Several strategic partners have been involved, including Cathay Pacific Airlines, United Airlines, and BP. The economics of this technology show that MSW conversion can potentially be very attractive. The required selling price is primarily controlled by the costs of the raw materials. Since one only need to pay for the sorting of the MSW feed, one receives a tipping fee credit from the landfill company, which make the raw material costs ignorable. The technology, however, is capital cost intensive, but even at an assumed fixed capital of $400 million, the required selling price would be $1.51 per gallon. Catalyst and chemicals, utilities, and fixed cost together account $1 per gallon per ton of product. Figure 31 is a simplified block diagram of a new European Union project. The target is to make dimethyl ether from biomass. The fledged consortium combines 10 legal entities from 6 European countries, including 3 universities, 3 research centers, and 2 complementary technology providers. As additional members, 1 industrial end user and 1 small medium-sized enterprise join the consortium. Biomass is pre-treated to reduce its size and moisture content. The biomass feed is then sent to a special gasification reactor system, with an added cleanup section. The clean syngas is converted into DME, using a novel fixed-bed tubular catalytic reactor. This reactor contains a porous sorbent that removes the in situ produced steam and enhances the DME yield. Additional hydrogen can be produced by water electrolysis, using renewable electricity. This enhances the DME production and supports the power-to-liquid conversion. The produced DME can be used as biofuel, and this will increase the sustainability of the automotive transportation sector, substituting conventional fossil fuels. The fledged reactor system combines a gasification reactor, to be integrated with a combustor reactor. The gasification reactor requires steam, and it produces mainly hydrogen, carbon monoxide, carbon dioxide, and char. In the gasification reactor, solid calcium oxide reacts with carbon dioxide, producing calcium carbonate. This allows to adjust the syngas composition to the specifications of the downstream DME reactor. In the combustor, residual char from the gasification reactor is burned with air, decomposing calcium carbonate back to calcium oxide and carbon dioxide. This slide is about anaerobic digestion. This is an emerging, attractive technology. Carbon-containing feedstocks like livestock waste, crop residues, wastewater streams, and food waste, are all converted in the presence of bacteria in a low-pressure reactor. One makes biogas and a digestion byproduct. The biogas can be used to make heat, electrical power, and biogas. The biogas is used to transportation or send as biosynthetic methane to the grid. The digestion byproduct has also attractive uses. Ultimately, most of the products end up as carbon dioxide again. For this reason, this technology is a carbon-neutral approach, at least to a large extent. Waste plastic products are becoming an environmental problem. At the Northwestern University, in cooperation with scientists at the Argonne National Laboratory and the Ames Laboratory, a technology is under development, making lubrication oil from plastic materials. their scientists propose to use platinum nanoparticles, on perovskite nanotubes as catalyst, for the hydrogenation of the plastic waste products. Figure 35 shows a paper bottle, with Pilsner beer made by the Carlsberg Brewery. The paper bottle is covered at the inside, with a thin layer of special polymer containing furane polyethylene. This material has been developed by Avantium in the Netherlands. The material is completely sustainable, because it is made from natural sugar. This thin layer has great gas permeability, needed for liquids like beer and carbonated soft drinks. The paper bottles can reduce the carbon footprint by 30%, relative to glass bottles. Avantium is pursuing similar applications for their special sustainable polymer. In reference 21, related to the publication by Paul Hawken, many approaches are listed to reverse the global temperature increase. Of special interest, education and family planning are highlighted. By applying this, we could potentially reduce carbon dioxide emissions by 109.2 gigaton, if applied during the next 30 years. One hopes that with education and family planning, the total world population will not increase as fast as projected currently.